Grade 11 Chemistry, welcome to Unit 2. Unit 2 is chemical reactions. We're mostly dealing with predicting what kind of reactions will occur when two chemicals are mixed and balancing those reactions. So we're going to go through a bunch of different ones. You can look at the schedule for the exact list. Here's what we're going to do. So today we're going to do a review of binary compounds. We'll talk about why chemicals react. We'll do an overview of the basic types of reactions, some kind of grade 10 review. Then we're going to talk about numbers and state symbols and what they mean in chemical reactions. And then finally we're going to get to balancing equations and a review of why we balance equations and some practice problems. So let's start off with a review of binary compounds. So far, all the compounds that you know how to name, like from the previous unit, are all binary. Right? Metal and a nonmetal, or a nonmetal and a nonmetal, or a polyatomic and a nonmetal, or a metal and a polyatomic, or a polyatomic and a polyatomic. Right? So sodium chloride, magnesium nitride, titanium 2 sulfide, H2O, dihydrogen monoxide, HF, hydrogen monofluoride, CCl4, carbon tetrachloride, polyatomic and nonmetal, so ammonium chloride, ammonium sulfide, ammonium phosphide, metal in a polyatomic, potassium nitrate, copper 2 sulfate, aluminum carbonate here, and then this ammonium chlorate down here. Notice that all of them have two names, binary, two names, and two parts, essentially is what binary means. So, there's lots of other types of compounds. They're not necessarily binary, but we're going to exclusively deal with reactions that rearrange and involve binary compounds, at least as starting materials. So they have two distinct parts. There's a name that reflects those two parts. And all of them are ionic except for the nonmetal, right? So these guys are molecular, but all these other ones are ionic. They have a positive ion and a negative ion and a ratio of positive and negative ions. And so because of this, identifying these ionic charges and these components and being able to do like the crisscross thing, predicting what the ratio is going to be a key to predicting what kind of reactions, what kind of products we're going to get. So that was a quick review. We're going to move to the second section, which is why do chemicals react? Right. Why chemicals react? So chemicals react because some bonds are more favorable than other bonds, and that's really the main reason here. And generally speaking, they're all trying to get to a lower energy state in some way. So typically that means that we're going to break a high energy bond and create a new low energy bond, and that's a more stable thing to be in, and that's why energy is usually released. It also makes it hard to reverse the reaction. So for an example of this, if I go over to the whiteboard, let's take say this reaction, right? Water, making water. We'll balance it out. You have hydrogen here. They're bonded, which is lower. Like this would be a high energy state. This is a high energy state. It's a high energy state. So this is lower energy. That's lower energy. Same thing with the oxygens. Right? This is a high energy state where they're separate. This is a lower energy state. But if this gets, if this creates this kind of thing, the oxygen can exert its electronegativity and pull harder. Right? It will go down to this energy state. And these bonds, these OH bonds, are lower energy than an HH bond or maybe an OO bond like that. So, you're making lower energy bonds, which means you're releasing energy. That's essentially what's going on. So lowest energy. Right. So this will go spontaneously. You might have done the hydrogen and oxygen like pop test when you're in grade 10 chemistry. that happens spontaneously, but we can make it go back. We can make it go back with an input of energy, right? If we put in some energy, we can actually take the water and turn it back into hydrogen and oxygen. They do this on the space station to make their oxygen. It's called electrolysis. One of the first really well-studied chemical reactions, interestingly enough. It's what led Dalton to create the law of definite proportions. I've got another example, which is an actual physical example, which is these guys. These are called bang snaps. They're little packets of rocks, basically, just gravel. They're very small. What you can do with them is, if you drop them, right, not a lot happens. But if you throw them, they blow up. And you see a little bit of like a little ash and stuff that gets left behind. So it's a chemical reaction that happens. You can tell it's a chemical reaction because there's noise and light and stuff. And if I do it right, I can do it in my fingers and you get some smoke coming out and some light and things like that. So it's a chemical reaction, and it also helps to explain this. With generally everything's trying to get to a lower energy state, because what these are something called silver fulminate, which looks like this. Silver and fulminate has this really weird structure. It's a carbon triple bonded to a nitrogen, single bonded to an oxygen. So this carbon is negatively charged, the hydrogen is positively charged, the nitrogen is positively charged, and the oxygen is negatively charged. It's really weird. It's a very strange structure. So this is bad, right? This is bad arrangement. So it's high energy. High energy. So it would much rather make stuff like, CO2. That's better. Or N2. Right? Or just carbon, just solid carbon. Right? These are very common, and they're lower energy. Right? Lower energy. So this is where the reaction comes from. This stuff is currently in that state, but if we give it a little bit of energy to break those first bonds, it can start rearranging into what is a lower energy state. So this thing will spontaneously react. One more time, come on. There we go. That was a good one. All right. So that is why chemicals react. They're going to a lower energy state. This is what makes it hard to reverse. But we can reverse it by putting in energy most of the time. All right. Next up in our list is an overview of the types of reactions. So I'm going to pause. So an overview of reaction types. This is an old note, so everything was based on Taylor Swift songs, but I think it's still appropriate. The first type of reaction that you might have learned is synthesis. So that's A plus B becoming AB. Now often A is like a metal and B is a non-metal, so you'll end up with a ionic compound, but this can happen with molecular compounds too. Let's do an example of this. So we're going to go over here. Right, so synthesis. Right, so for example, we take sodium and we add chlorine. Note that chlorine is a Hofbrinkel element. The Hofbrinkel elements, these ones, Hofbrinkel, HOFBRINNCL, form diatomics in nature. So that's where the 2 comes from. And that'll make NaCl, right? How do we know it makes NaCl and not something else? Well, sodium is going to make a +1 ion, chlorine is going to make a -1 ion, so together those 2 are going to make NaCl, right? It's that crisscross thing. that crisscross thing, or you can just, run it through how many numbers of each do I need to make it work. And you see, we have to balance this. We need two sodiums. We're gonna make 2 salts, right? So that's an idea. That's a ionic, meaning an ionic. So metal meaning a non-metal, making an ionic compound. We can also have synthesis between nonmetals, just like that H2 plus O2 thing that I diagrammed earlier. That one, right? That's a nonmetal and a nonmetal. We can't predict that one, except for maybe with structures. You might be able to predict that one with structures. Okay, so that's synthesis. That's the first kind of thing. From synthesis, the natural one to talk about afterwards is decomposition. So decomposition is the opposite of synthesis. You have something that's together, and then it goes apart. Right, AB to A plus B. This is less common because usually things are together because it's a lower energy form, so why would they break apart? But it does happen on occasion. This is a decomposition reaction. There's one example of a decomposition reaction. So AB to A plus B is a common one for binary unary. We will cover some of these where it's actually 3 parts that split into unequal parts. So we'll talk about those later. That's on Tuesday. So that's a decomposing compound. Maybe one example of a decomposition that we could do is I don't know. If you take sodium chloride and you melt it, liquid sodium chloride, and you can actually bring it back out to sodium plus chlorine. Liquid sodium and chlorine gas, you can actually separate it back out, and obviously we'll need to balance that. So that's a decomposition reaction. Another one that's pretty common is like baking soda, which when you heat it up will decompose into or actually I think it's Na plus CO2 plus H2O. No, that doesn't make sense. Something like that. But yeah, it's a decomposition. Sometimes that happens at very high temperatures as decomposition. Then we've got our displacements. We've got single displacement, where the Taylor Swift song is "You Belong with Me." The guys with this girl, Taylor Swift's like, "Oh, I wish I was with him instead," and then it's basically that. It's A is with B. Presumably A is positive and B is negative. D comes in, D is negative, so D takes B's place. So this is a negative replacing a negative. Or you can have the positive, right? A is positive and B is negative. C is a positive, it'll replace A. So a positive will replace a positive, or a negative will replace a negative. And that's a single displacement. In British, it's sometimes called single replacement. You'll see it as single replacement sometimes. There's a lot of examples of this. A classic one in chem labs is silver nitrate plus copper. Silver nitrate plus copper, the copper will displace the silver and become, the copper will take silver's place and typically make a +2 ion, and then the silver will stay behind. So you see that the copper, which is positive, right? It's a metal, will replace this silver metal, right? They're kind of switching places here. So that's a single displacement reaction. And then the next one is double displacement. Do keep in mind for single displacement, again, positive replaces positive, negative replaces negative. And then the last one is double displacement. I don't think Taylor Swift has written a song like that yet, because it involves 2 things: swapping partners, and I don't think the world is quite ready for that song yet. But yeah, the two compounds swap their positive and negative. So it's AB plus CD becomes AD. Note the positive and the negative got together because that's how it works. And BC gets together. The negative B gets with the positive C. So generally this happens in aqueous environments. So you have two dissolved salts and they'll rearrange. And I think there might be some limited examples of this happening in powders, but it's almost always in an aqueous environment where things are free to move, and both of these are free to move around. Like, it's not like AB, it's actually A plus and B minus, and they're separate and they're like moving around, and then like B bumps into C and is like, hey, I like that, and B and C get together. It's a lower energy state for B and C to be together than A and B to be together, stuff like that. So that's a double displacement. And please note that these types all have different kind of starting materials. So we can actually tell what kind of type it's going to be without seeing the whole equation, right? If it's A plus B, well, it's got to be synthesis. If it's AB and it's just AB, well, all they can do is fall apart. If it's AB plus C, right, and C is like a positive, then it's going to single displace. If it's AB plus D, and D is a negative, right, C plus C is like a metal and D is like a negative, it's going to be a negative replacement. The D is going to replace the B. Here the C is going to replace the A. And if it's AB plus CD, it's probably going to be double displacement, where maybe the negative swap or maybe the positive swap, you get to decide how they're going to swap, especially if these are aqueous. Thank you. So yeah, generally speaking, you can tell what they're going to be just from the start, how it starts. So synthesis, decomposition, single displacement, a positive switch. Here's a single displacement, which is a negative switch, and this one's going to be double displacement, a double displacement reaction. So yeah, we can use these archetypes to predict it. Okay, that. Now a few more that you might have learned and might not have, but we're going to cover them. Neutralization, which is an acid plus a base, and it's going to create an ionic compound and some water. Our conception of acids and bases for our unit is going to be that acids contain H plus and bases contain OH minus. There are other types of acids and other types of bases that don't contain H plus and bases that don't contain OH minus, but this will be good enough for us for this unit. We'll talk about some of the exceptions later in the course. Right, so you got an acid, you've got a base. It's going to be actually a double displacement. Neutralization is just a type of double displacement. The hydrogen is going to meet the OH and make H2O. The sodium is going to meet the chloride and make NaCl. So it's just a double displacement. It's the same archetype as that. If you compare that to this, that's literally what's happening. AB, CD, right? And then A gets with D, so A gets with D, that's H2O, HOH, and Cl gets with Na, so NaCl. So that's neutralization reactions. And then combustion reactions. Sometimes you see combustion reactions in grade 10 science, sometimes you don't, but what you can think of them as, it's just a fire. So what does fire need? It needs oxygen, it needs fuel, oxygen and fuel, oxygen gas, and the fuel is going to be something that's flammable, usually carbon based. What is produced in a fire? Well, we know it's carbon dioxide, and you get other products, and one thing that you might not know is that water is actually produced. So Here's the basic combustion reaction: is a hydrocarbon plus oxygen becomes carbon dioxide plus water. Now, a hydrocarbon is exactly what it sounds like. It's carbon and hydrogen. There's a bunch of different kinds of hydrocarbons. Candle wax is a good example of a hydrocarbon. It's just carbons and hydrogens. But if you burn it, you end up with carbon dioxide and water. Yeah, carbon dioxide and water. There's other things that combust, like, you can burn a marshmallow and that's sugar, and that's got like, C12H22O11. There's like more stuff that'll burn. But it's hard to balance. We're not going to bother with balancing combustions that have extra oxygens in them and stuff. That's fine. We'll just use pure hydrocarbons when we do combustion reactions. So there's going to be more about combustion reactions on next Thursday, the 14th. So yeah, wait for that. Now we're getting into our last piece, which is about balancing, so numbers and state symbols and balancing. So I'm going to pause and get that set up. All right, numbers and state symbols. The big numbers in an equation, they tell us the relative numbers of that substance. So I'll put this down here. Relative number of each substance in the equation. So for example, when we have 2Mg plus O2 becomes 2MgO, that 2Mg is telling us we have 2 magnesiums. Meanwhile, the small number, right? The small number is for the element, so the 2 here means we have 2 oxygens. This might not seem like a big difference right now, but it is important when we have something like this, right? 2MgO. So 2MgO means we have 2 magnesiums and 2 oxygens. You can imagine it's like a pack, 2 packs of MgO. So this tells us in this reaction we need twice as many particles of magnesium as we need molecules of oxygen, because 1 molecule of oxygen has 2 oxygen atoms in it. And so it's going to become very important in Unit 3, which is stoichiometry, to tell the difference between big numbers and small numbers, but it's going to be important for us here too. So let's put up an equation, and we'll explain why it's important. So, let's do Mg plus I'll do HNO3. Let's make it a little bit complicated. Here we have, you might call it hydrogen nitrate. It's called nitric acid, but you can call it hydrogen nitrate. So there's a positive and a positive. They're going to swap. We're going to end up with MgNO3, but magnesium is a 2 plus, and NO3 is a 1 minus. So we need 2 NO3s plus H. And we know that H, being a Hofbrinkel element, makes H2. And so what we have to do then is put a 2 in front of here to show that we have two NO3s to match our magnesium. 2 NO3s to match our magnesium. That's what that 2 is saying. 2 for the whole thing. And we have 2 hydrogens. Right, those 2 hydrogens are going to make our H2 molecule. Those 2 are going to make that. And then this is just going to be Mg2 plus NO3 minus NO3 minus. Right? So we have the same numbers on each side. So that 2 tells us that the entire thing gets multiplied by 2. Really think about it like a block that you're multiplying by 2. It's the only thing we can change in a chemical reaction. If we change any of these numbers, right, any of these little numbers, the chemicals themselves are going to change. The compounds themselves are going to change, and it's going to be a different reaction now. So we're not talking about the same reaction. We can only change these front numbers. And then state symbols. State symbols tell us what state the reactants and products are in. These are the state symbols: solid, liquid, gas, and then there's aqueous. So I'm sure you know solids, liquids, and gases, but aqueous is sometimes a tricky one. Aqueous means dissolved in water. Now, dissolved and aqueous specifically means like a solution, right? Think about it like, I don't know, apple juice, right? Apple juice looks like just one liquid. It's transparent, and you can't tell that there's individual particles in there. As soon as you see individual particles, it's no longer aqueous. That's solids dissolved in the water. So, yeah. So something like apple juice is aqueous, but something like, I don't know, sand that's suspended in the water is not going to be aqueous. That would get solid. It would be a solid. Right. We have to add these state symbols to tell us what states we're in. It helps us talk about what kind of things to expect out of our reaction. Like if there's a gas that's going to come out of my reaction, I want to know that as a chemist. If it's soluble in water, I want to know that as a chemist. If I have to have it dissolved in water to make the reaction happen, right, so that the ions are free to move, I want to know that as a chemist. So we put these on our reactions to give more information to other chemists that might be trying the same reaction. That's numbers and state symbols in chemical reactions. We're going to be putting those. And now we're going to talk about balancing equations. So pause. Okay, why balance equations? Why do we do this thing called balancing equations? Well, it helps us understand the relative amounts of each chemical that we need to put into the reaction. And it goes all the way back to Dalton's atomic theory. So for example, here's the synthesis of H2O. 2 hydrogen plus oxygen becomes 2 waters. There's actually a lot of rocket engines that burn hydrogen as their fuel. So they have a hydrogen tank and they have an oxygen tank. They have to bring their oxygen with them because there's no oxygen in space. So if they want to get around or change velocity in space, they're going to need to make a combustion happen. And also because they need a lot of oxygen to burn all that hydrogen, so they can't take it out of the atmosphere. But the numbers give us the relative amounts. Here we see that we need 2 hydrogen gas for every 1 oxygen gas. And if we look here, here's an actual picture of a rocket that uses hydrogen fuel. Look at the size of the fuel tanks. Right, there's the hydrogen tank. There's the oxygen tank. It's 2-to-1 ratio. It tells us that that tank needs to be twice as big as this tank in order for in order to have the optimal amount of fuel. If you had, if these ratios weren't like that, you might have too much hydrogen or too much oxygen or whatever. So it tells us the best mixture, and that's why we balance our equations. We want to be exact. We want to know how much of each thing to put in order to get a good reaction. Right. So here's the rules. Right, the number of atoms on each side of the arrow must be equal, and the most important rule is that you can't change the little numbers. Right, we can't change the subscript numbers, the little numbers, because that would change the compound, and we don't want to change the compound. We want to do this reaction with these two elements, these two compounds that are reacting with each other. If we change the small numbers, it's not the same reaction anymore. We can only change the coefficients, which are the big numbers. The big numbers are the coefficients, which is the relative amount. I can double how much magnesium I'm putting into my solution. That's no problem, and that's why we can change the number at the start of the thing. That's why when we change one of those big numbers, it'll multiply every atom in the compound by that number. Right? Every atom in the compound by that number. A lot of different structures and different techniques for balancing equations. I'm sure you can find some if you look them up. I prefer just making a little accounting list of how many elements are on each side, and just going from there. So next up, we're just going to do some practice problems. We'll maybe spend about 5 minutes practicing some equations, and then that'll be the end of the video. Here is our first practice problem. This is the equation. KCl3 becomes KCl plus O2. So note that the O3 became an O2. What kind of reaction is this? It's a decomposition. It's a decomp. Because we just have one thing on this side and it's splitting into 2 things on this side. And we're going to look at balancing it. My way that I like to do is I just draw a line down the center and I go, hey, there's a potassium, there's a chlorine, and there's 3 oxygens right now. There's 3 oxygens. So there's right now there's 1 potassium, 1 chlorine, and there's 3 oxygens. On this side I have 1 potassium, 1 chlorine, and 2 oxygens. So it can help me see where I need to work. Right now, potassium's good, chlorine's good, but there's this imbalance between the oxygens. I need to get the oxygens to the same number. That way I have the same number of oxygens on one side as the other side. And you know, with a little bit of math, you might spot the common denominator thing that's going to happen here. If I multiply this by 3, if I go times 3, that's going to be 6. Go this times 2, that's going to be 6. In order to multiply that by 2, I have to put a 2 in front of that whole thing. And remember that when I do that, it multiplies the entire compound by that. So that 2 is going to go this times 2 and this times 2. So that's going to be 2 of those and 2 of those. Now this, I multiplied it by 3. I multiplied it by 3. There's my 3. That only affects the oxygen. Right? That only affects the oxygen. And now there's 6 oxygens there, so I'm good for that. But now I've got these. These are not balanced. There's 2 here and 1 here. Seems easy enough to fix. I'm just going to multiply this by 2. And when I do that, I multiply the entire thing by 2. I multiply the whole block by 2. So times 2 and times 2. So that's 2 and 2. And now we're good, right? The 2 matches the 2. This 2 matches this 2. This 6 matches this 6. And I have balanced my equation. So yeah, it takes 2 KClO3s, makes 2 KCl's, and makes 3 O2s. I'm going to get, 1.5 times more oxygen than the KClO3 I put in. That's a relatively simple one. We're going to go to the next one. This is our next one. What kind of reaction is it? Well, we have a binary here and a single. The carbon went over and took iron's place, right? The carbon is now with the oxygen and the iron's by itself. As my old high school teacher used to say, something starts single and something ends single. So this is single displacement. Specifically on the positives, right? The positive side of things changed. And we have to balance it. So, let's look down our list. Let's make our little thing. This one's a little bit more complicated. We have 2 irons. We have 3 oxygens. We have 1 carbon. Here we'll write the same things, oxygen, carbon. Here we have 1 iron, we have 2 oxygens, and we have still just the 1 carbon. So a few other tricks that we can use here. This carbon's by itself, it's very easy to fix later. This iron is by itself, it's very easy to fix later. So any elements that are by themselves are relatively easy to balance. So I would say here, start with that oxygen again. 3 versus 2. The only way to do this by multiplying is to multiply this by 2 and this by 3. When I multiply this by 2, I have to multiply this entire thing by 2. Right? That's something that's very important to remember or keep in mind. When we multiply by 2, that also times 2 becomes 4. Right? This becomes 6. This becomes 6. And I'm multiplying this entire thing by 3, right? By 3, that's what I'm multiplying it by. So that'll affect my carbon count. This carbon times 3 is going to be 3 now. There's 3 carbons because we multiply the whole block. Okay. So oxygen's good. Now this is where the magic happens. Remember that since carbon's by itself and iron's by itself, they're very easy to fix now. We have 3 carbons on this side. We have 1 carbon on this side, but it's by itself. So to get 3 of them, you just multiply it by 3. You just throw a 3 in front of there, and you've got your 3 carbons. Now that's good. Same thing with the iron. We have 4 irons on this side, 2 Fe2, right? 2 times 2 is 4. So 4 here. A single iron here, but we can just multiply it by 4. And now irons are good, oxygens are good, and carbons are good. And our equation is balanced. 2 Fe2O3s plus 3 carbons, 4 Fe's plus 3 CO2s. We're going to do one more practice. This is our last one. I chose a more complicated one just to show you that the technique works for complicated ones as well. This starts off looking like a double displacement. It's a positive and negative and a positive and negative, and indeed it is a double displacement. But then after that it kind of decomposes. So don't worry too much about the type of reaction here, but we can still balance it. We can balance it without knowing what type it is. So we'll do the same thing. We'll run the same scheme here. We've got one calcium, we've got carbon, we've got one of those, and oxygen, we have three of those. We have one hydrogen, and we have one chlorine. One hydrogen, one chlorine. Now on this side, it's going to be interesting because that oxygen splits into H2O and CO2. But that just means we have to be more careful when we are keeping track of our elements. Calcium, we've got one. I like to keep the same elements in the same order so that it's easier to keep track of. So carbon here, we have one. There's our one carbon. Oxygen is our next one here. So oxygen should be next one here. We have three of those already. Hydrogen, we've got two. And chlorine here, we have two. So this looks like a difficult thing to balance, but it turns out that the only imbalance that we have is down here. Right? This is where the accounting thing is really, really helpful. One calcium, one calcium, one carbon, three oxygen, three oxygen. And the difference here is that this has one hydrogen and one chlorine. This has two hydrogens and two chlorines. And wouldn't you know it, we have this handy HCl there. So the answer is just to throw a 2 in front of HCl. This looks like a difficult equation, difficult reaction to balance, but it's really not that bad. And laying it out like this can really help us figure it out. Now that 2 is going to multiply both of these because it multiplies the block. That's 2, and that's how we balance that equation. There's a worksheet that you can try for a bunch of different ones, yeah, that's it for today's lesson. Thanks for listening.